We'll start with the meeting. So today we will just revise the second chapter, curve tracing, in which we broadly classified our curve in two parts or two types. First one was Cartesian curves, and second one were polar curves. I'll just drag this down. So while studying these curves, we discussed some properties of these curves, and using those properties, we defined or we draw the curve. The first property in both the curves were symmetry. So here also we discuss first symmetry. So in the symmetry, in Cartesian curve, we discuss that when a curve is symmetric about x-axis when we can replace y by minus y. It is symmetric about y-axis when we can replace x by minus x, and it is symmetric about origin when we can replace x and y simultaneously by minus x and minus y. There were some curves which was symmetric about x is equal to y line, and to check that we could replace x by y and y by x. So interchange the role of x and y, and if we get the same equation, they were symmetric about x y line. Then to discuss the symmetry in the polar curves, we said it is symmetric about the pole. The pole is the point which is quite similar to or acts as similar to origin in the Cartesian plane. So it is symmetric about pole when we can replace r by minus r. So even powers of r were present. So in such cases, we said it is symmetric about the pole. Later we said it is symmetric about some line theta is equal to theta is equal to, let's say, 2x, or theta is equal to x if we can replace if we can replace theta by 2x minus theta. So starting with theta is equal to 0, if we can replace theta by minus theta, it is symmetric about initial line, that is theta is equal to 0, and so on. The second thing that we discussed in both the cases were the starting point. Here it was called as an origin, and here we called it as pole. So it was a distance 0 point. So notice that the coordinates in this case are r x y, and here are r theta. So x is the distance in x direction, y is distance in y direction. Here r is the distance from pole, and theta is angle made with initial line. So here we check if the curve is passing through origin or not by directly substituting the value 0, 0 in the equation. By, the, by substituting this value, we got the value if the curve is passing through origin or not. Here we check values of pole. We calculated the values of pole as theta corresponding to r is equal to 0. Later, if the curve is passing through origin, we calculated tangents at the origin, and here we calculated tangents at the pole. Tangents at pole. So calculate tangents at the origin, we equated the lowest degree terms with 0, and here to calculate tangents at the pole, we take the values that we got in this second point while calculating the pole as theta. We said those values of theta are the poles at the origin, or tangents at the pole. Later, we discussed existence or region of existence. Region of existence. So we discarded some region in which curve may not lie, or curve will not lie. Here, again, the same thing, region of existence. So here also we discuss same thing, region of existence. But since our curves were finite, in this case, we were able to calculate R max and R min. So they were the maximum and minimum radius circles in which our curve lies. So by using this R max and R min, here when we calculated the intercepts or the intersection with coordinate axis, we calculated the points corresponding to this of some points. So here we calculated theta corresponding to R max and R min. So they were something similar to our intercepts in Cartesian coordinates. Then later we calculated tangents at the intercepts, tangent at intercepts, and here we calculated tangents, but those were not the regular tangents, or slope was not counted with this x-axis. They're they're calculated as radial tangents. So the angle between radial vector and tangent vector was calculated at R max and R min. So at this point, we calculated tangents here. Finally, here we calculated the asymptotes. Asymptotes were defined as slopes, tangents at infinity. So asymptotes. Here there were no asymptotes. There were no asymptotes. So we did not discuss anything because curves were finite. Curves were finite. So there were no asymptotes in this case, in polar case. And finally, we, we draw some table value. Here also again some tabular value. And finally, we drawn the graph using all the information that we got. So notice that you can see we are doing something similar in both the cases. We are discussing the symmetry, then starting point as origin. If there is the origin existence of the origin or curve passes through origin, we calculated tangent at the origin. Here we calculated if our curve passes through pole or not. If it is passing through pole, what are the tangents at the pole? Region of existence in both the cases. Intercepts, instead of intercepts, we just say we should calculate the theta values corresponding to R max and R min. We can also calculate some R values corresponding to certain thetas like pi by 2, pi, 3 pi by 2, because those are some important points that we know. So we can interchange the rule, just substitute that value of theta and calculate the R corresponding to it. Here we substitute in to calculate theta corresponding to R max and R min, we substituted the value of R max in the given equation. We'll see this in the examples. So we will use this information to plot certain graphs. So we'll start with the Cartesian graph given by this equation: y square into a square plus x square is equal to x square into a square minus x square. You can see that this is the second or third question in the assignment sheet. So that's the same question I'm going to discuss here. So let's write down this given equation as is, I'll just rewrite this equation as x square into y square plus a square into y square minus x power 4 plus x power 4, because when it comes to the left hand side, this quantity will be positive, and minus a square x square is equal to 0. So I'll start discussing, or I will call this equation as f of xy so that it's easier to address the equation. So I'll start discussing about the symmetry. I'll start discussing with the symmetry. So notice that all the powers of x and y that we can see all are even. So it is symmetric about both the axes. Since all the powers for x and y are even, the curve it's symmetric about both the axes. both the axes. So it is symmetric about both the axes. So we need to draw the curve in, let's say, first quadrant only, so that we can know what how that curve behaves or how that curve looks in all the Cartesian plane. So we will keep this point in mind. So we need to draw the curve in the first quadrant only. Second point, we'll discuss about the origin, or if the curve passes through origin. So to discuss about this, we will substitute the value of as x is equal to 0 and y is equal to 0. Notice that this term will be 0, this will be 0, this will be 0, and this will be 0. So f of 0, 0 is 0. So therefore, equation or 0, 0 satisfies the equation. 0, 0 satisfies the equation. Since 0, 0 satisfies the equation, we can conclude that the curve passes through the origin. Passes through the origin. Now, since the curve is passing through origin, there is a point, or we can discuss about tangents at the origin. We will discuss tangents at the origin. So to discuss the tangent at the origin, we need to equate, or we need to equating lowest degree terms of f of xy with 0. So notice that our f of xy is given by this equation. So here is a degree 4 term, degree 2 term, degree 4 term, degree 2 term. So we need to equate degree 2 terms with 0. That is a square y square minus a square x square is equal to 0. And therefore, y square is equal to x square, or we can conclude y is equal to plus or minus x. Notice that we are getting two different tangents. So origin is a double point and it has two different tangents, so it is a node. Therefore, origin is a node as it has two different tangents, two different tangents passing through it, passing through it. So origin is a node. So we could discuss something about origin. Now let's discuss about some intercepts. So we will start discussing about the intercepts. Even though in the above table I said we should discuss about existence of the region of existence, but that order does not matter. So for intercepts, let's calculate x-intercepts first. So for x-intercepts, we know we need to substitute y is equal to 0 in the given equation. So notice that given equation is this one. So if I substitute y is equal to 0, this term is 0, this term is 0. So I have x power 4 minus ax square minus x square is equal to 0. Therefore, x square in bracket a square minus x square minus a square is equal to 0. So the values for x I will get are x is equal to 0, x is equal to 0, x is equal to a, or x is equal to minus a. So notice that since x was a double point or origin was a double point, we get these repeated values. So this also confirms that origin was a double point. Origin was a double point. And we get two different new intercepts. So these intercepts corresponds to a comma 0 and minus a comma 0 are intercepts. So these two are the new intercepts that we got. Now let's calculate y-intercepts. So to calculate y-intercepts, we need to substitute x is equal to 0 in the given equation. So this is my given equation. So this is my given equation. I will just again copy this with equal to 0. So this is my given equation. If I substitute x is equal to 0, first term is 0, second term will survive, third term is 0, and this term is also 0. So notice that I will have a square y square is equal to 0, and therefore y is equal to 0 or y is equal to 0. So repeated values, and these values are actually corresponding to double point as origin. So origin was the double point. So x is equal to 0, y is equal to 0, x is equal to 0, y is equal to 0. So that's why we got double values for y. So this is also confirming that y, our origin was a double point. But we did not get any new information in y direction. So only x-intercept exists, and new intercepts exist, and they are a comma 0 and minus a comma 0. Since we got some new intercepts, we should calculate tangent at those intercepts. So we will calculate tangents at intercepts. So tangent at intercepts. So to calculate tangents at the intercepts, again start with the given equation, differentiate this equation because tangents are the slopes, right? So we can tangents are at last they are some lines, so we can describe them in as a point slope form. So we know the point because that's the point on the curve. So we just need to calculate the slope. So to calculate the slope, we are differentiating with respect to x because dy by dx gives us the slope. So if I differentiate the first quantity, I have 2xy square plus 2y x square into dy by dx plus 2a square y into again dy by dx plus 4x cube minus this is 2a square x is equal to 0. So all the terms which have dy by dx as coefficient, I will just club them down in one bracket. So 2a square y is equal to, and I will shift other terms to my right hand side. So 2a square x minus 4x cube, and then this term, so minus 2x y square. So therefore, value for dy by dx is 2a square x minus 4x cube minus 2xy square divided by 2xy 2yx square plus 2a square y. So notice that we want to calculate at a comma 0 and minus a comma 0. So dy by dx at a comma 0 is given by, notice that there is a y sitting here, so denominator will be definitely 0, and this will be, if I substitute the a, this term will get cancelled, so this will be 2a cube minus 4a cube, which is minus infinity, and dy by dx at minus a comma 0, just verify that this will be plus infinity. So therefore, tangents at both the points a comma 0 and minus a comma 0 are perpendicular, or instead of perpendicular to x-axis, I should say parallel to y-axis. They are parallel to y-axis. The slope is infinity means they are creating the 90-degree angle with x-axis, and the axis which actually creates the 90-degree with x-axis is the y-axis. So we got tangents at the intercepts. So now let's discuss region of existence. 6. Region of existence. So again, start with the given equation. Notice that we cannot solve x in terms of y because there are different powers of x like x square, x power 4, x square, and so on. So it's difficult to solve x in terms of y, but we can easily solve y in terms of x because only y square terms are present. So I will rewrite this equation as y square is equal to this a square x square minus x square x power 4 divided by x square plus a square, and therefore y square is equal to y square is equal to or y is equal to square root of this quantity, the same quantity again, square root of a square x square minus x power 4 divided by x square plus a square. So since we are taking the square root, we will discard the region in which this square root is negative. This square root and whatever the quantity that resides in this square root, this quantity is negative, we will discard such regions. So I'll use the wavy curve method, which you have done in class 12, just to calculate quickly. Otherwise, you can go for substitution methods. So I will calculate the zeros of my numerator. So zeros of the numerator are 0, a, and minus a, which we have calculated already. And notice that multiplicity associated with them is 1 here. For 0, it is 2, and minus a, it is 1. And when at plus infinity thing, when we go for plus infinity, the leading coefficient here is minus x square x power 4, so it is negative. So numerator will be negative, denominator will be leading coefficient is positive, so it will be positive, so whole quantity will be negative. Since we have encounter odd multiplicity point, the next in this next region sign will be positive. We again encounter even multiplicity point, so sign will not change. And when we again encounter the odd multiplicity point, sign will change. So from this point, we can conclude that the region in which this curve lies is given by this graph. So there is x is equal to a line, there is x is equal to minus a line, and beyond which the curve does not lie. The curve lies in this central region only. The curve lies in this central region only. So I'll add a page to discuss about my asymptotes. So to discuss about the asymptotes. So to discuss the something about asymptotes, again we will start with the given equation, and we will note that the degree of f of xy is 4, which implies it can have at most 4 asymptotes. It can have at most 4 asymptotes. So to calculate those asymptotes, we should start with calculating our helper functions, helper polynomials, phi 4m. Well, uh, in this case, to calculate phi 4m, collect all degree 4 terms with the condition y substituting y is equal to m and x is equal to 1. So the first term will give me y m square and second term will give me plus 1. I don't need to calculate further because I can't solve this phi 4m equal to 0 for values of m in real line. So I won't be calculating phi 3m, then phi 2m, and phi 1m. And I won't be calculating these quantities as phi 4m is equal to 0 cannot be solved, cannot be solved in R. So there are no, so this actually concludes there are no asymptotes, there are no asymptotes, asymptotes of the type y is equal to mx plus c. Note that this was the slope for which we were calculating. Since this slope does not exist, there is no asymptote of this type. So since But notice that these lines does not corresponding to the calculate the lines which are parallel to y-axis. So there is still possibility that still possibility that asymptotes asymptotes are parallel to y-axis. To check that, we'll again start with our given equation and we'll equate the highest degree y coefficients with 0. Notice that the highest degree for y that is appearing here is y square. So collect the coefficients of that x square plus a square and equate to 0. Notice that this also we cannot solve. So there are, since above equation cannot be solved in R, above equation, above equation cannot be solved in R. There is no asymptote which is parallel to y-axis. So this curve has no asymptote as such. So we can conclude that this curve has no asymptote. So to calculate some tabular values, to reduce the time, I have already calculated these values. So I will just copy that table from my previous notes. So I guess I have calculated not in the curve tracing. I guess I have calculated them in the assignment. So not this one. Okay, so this one's. I'll just copy this table. And here for simplicity, I have taken a is equal to 1 to draw the tabular values. So again, I need some more space. So I will just add a page. And I will give you the table. So you can plot this table or this. You can get this table from your Calci, or you can also use some programming, but that is not allowed in the exam. Actually, I have drawn this table using Python. So you can plot these tabular values. And now, finally, we'll plot the graph. So first, we'll start with our axis. These are our x-axis, and this is y-axis. So we'll start with our axis. Now, we'll first draw our tangent at the origin. So the tangent at the origin where this x is equal to plus or minus x, y is equal to plus or minus x. So I will plot these 2 points or these 2 lines. So y is equal to plus or minus x. So something like this line, and a line which is looking something like this one. Why it is not taking the shape, I don't know. So these 2 lines. So these are my tangents at origin given by y is equal to x and y is equal to minus x. Then I have 2 intercepts, namely at value a. So I have calculated at distance 7. No, I will calculate at let's say 8, and here also at distance 8. So I will call this point as a comma 0 and minus a comma 0. And I know at these points I have a tangent parallel to y-axis. A tangent parallel to y-axis. So I'll draw those tangents. Now, what I know about the curve, curve does not lie here, curve does not lie here, and this line has to be a tangent. So curve must start something like this way. right? And then while reaching at the origin, this y is equal to minus x should be a tangent. So I will start again like this and I will reach like this one. Again, I will use the symmetry, or well, I have drawn in one quadrant, so I know it is symmetric about both axes. So the mirror image will be there everywhere. So this part and this part, I can draw this because of the mirror image. This should be tangent to this axis or this line, and this one tangent with y is equal to x again. This is tangent with, or I will just plot that part again. So this line should be tangent with these two lines. So this is the graph that we got for our given equation. So not this. I will just copy the given equation again from the start. So for this given equation, we have plotted our approximate curve. So you can verify this curve in GeoGebra or in Desmos or any other software. You'll get a similar shape. Okay. So I guess you are now understood how we are going to calculate or how we are going to draw Cartesian coordinates or Cartesian curves. Now let's start with some polar curves. I'll go with the basic one. This is again similar to our that assignment problem. In the assignment, I have given r is equal to a sine 2 theta. So instead of sine 2 theta, I am just changing it as cos theta to discuss with you. Okay. So again, this curve, we can recognize this as Rhodes curves. And since this is a Rhodes curve, we know its shape. It will have some number of n numbers of petals. So here, number of n, or the n here sitting here is an even number. So it will have 2n number of petals. So approximate shape for for this curve will be something like this one. Okay, something like this one. So we got some idea about our curve. So we'll start discussing about the curve from the scratch. So let's discuss about the symmetry. So notice that a sine 2 theta. In this case, we can replace theta by minus theta because cos function is there. So since we can replace theta by minus theta, it is symmetric. It is symmetric about theta is equal to 0. Notice that we are replacing theta by 0 minus theta. So it is symmetric about theta is equal to 0 or initial line. Initial line. So again, notice that we can replace theta by pi minus theta. Again, since we can replace theta by pi minus theta. Notice that if I replace theta by pi minus theta, it will be r cos of 2 times pi minus theta, which will be r is equal to a into cos 2 pi minus theta. Again, this will be a cos 2 theta minus 2 theta, which is again a cos 2 theta. So we will get the original equation. So since we can replace theta by pi minus theta, it is symmetric about theta is equal to pi by 2. So half of the angle which is sitting here. So theta is equal to pi by 2. So it is symmetric about similar to both the axes in our Cartesian plane. So it's enough to calculate the graph in the first quadrant only. So now we'll discuss about the pole for this curve. So for pole, we need to put r is equal to 0. So I will copy the equation. I'll rewrite the equation here in white. So r is equal to a cos 2 theta. I will just copy this equation and will not paste it here. I'll just copy this equation and put r is equal to 0. So since we are substituting r is equal to 0, we have 0 is equal to a cos 2 theta. Therefore, cos 2 theta is equal to 0. So since cos theta is taking the 0 value, we know 2 theta will be an odd multiple of pi by 2. So therefore, theta will be an odd multiple of pi by 4. So calculate the different values in our one rotation, that is 0 to 2 pi. So in one complete rotation, we'll have theta is equal to pi by 4. Then if I substitute the 1, I will have 3 pi by 4. If I substitute 2, I will have 5 pi by 4. And finally, when I substitute the 3 value, I will have 7 pi by 4. So these are my tangents at my origin. So these are my pole values and also the tangents at my pole. Tangents at pole. So same values for pole, same values of pole acts as tangents at pole. That is theta is equal to these values again, pi by 4, 3 pi by 4, 5 pi by 4, and finally 7 pi by 4. So later we will calculate region of existence. Region of existence. So to calculate region of existence, we'll start with the given equation. So we have r is equal to a times cos 2 theta. We know that minus 1 is less than or equal to cos 2 theta is less than or equal to 1. So therefore, if I multiply by a, I will have a less than or equal to a cos 2 theta is less than or equal to a. And we know this middle quantity is r. So minus a less than or equal to r less than or equal to a. So we get r max as a and r min as minus a. So we got two values, r max and r min. So now what we can conclude from here is that our curve lies in the circle of radius. This radius has to be a. So curve does not lie outside this circle. So that's what we have concluded from this point. Now we'll calculate values. So values of theta corresponding to r max and r min. To calculate the values corresponding to r max and r min, you can write down the given equation. And for r max equal to a, we have a is equal to a cos 2 theta. So therefore cos 2 theta is equal to 1. So we have 2 theta, 2 theta as multiple 2 theta as even multiples of pi. So 2n pi, and therefore theta is a multiple of pi. So in one complete rotation, we have theta is equal to 0 and pi. So these are the values corresponding to R max. Now for R min was minus A. So for that, again, I will substitute minus A is equal to cos 2 theta. So therefore, I will have this cos 2 theta as minus 1. So this will give me cos 2 theta as odd multiples of pi, and therefore theta will be odd multiples of pi by 2. So in one complete rotation, I will have two different values. Theta is equal to pi by 2 and theta is equal to 3 pi by 2. So I got my values corresponding to R max and R min. So let's calculate the tangent at this point. So radial tangents or tangents with given vectors. Again, start with the given equation. Notice that we calculate the angle between radial vector and tangent vector as tan phi is equal to r into d theta by dr. So we want to arrive at this equation. So we will differentiate with respect to theta. So we have dr by d theta as differentiation of cos is minus sine, so minus 2a sine 2 theta. I need to take the reciprocal. So d theta by dr is 1 upon minus 2a sine 2 theta, and I need to multiply by r. So I'm multiplying by r to the both sides. So notice that r is equal to a cos 2 theta. So that's how I am multiplying. So finally, this left hand side is tan phi, and it is given by, we can cancel out a. So we have 1 upon 2 cot 2 theta. 1 upon 2 cot 2 theta. So we need to calculate radial tangents at these 4 points, 0, pi, then pi by 2 and 3 pi by 2. So we'll start calculating tan phi at a comma 0. So if I substitute the value 0, it will be infinity. Or notice that for all those values, this is mod a comma some n multiple of pi by 2. And I'm again taking the modulus of this thing. So notice that all those values will be infinity, and I can conclude that the radial vector, the radial vector at this n pi by 2 or n pi by 2 angles is perpendicular to its tangent, to its tangent. So since the slope is infinity, we can directly conclude that tan phi is infinity. So phi is pi by 2. So that's why they are perpendicular with each other. So radial vector and tangent vector are perpendicular at all those 4 points. So n is equal to 0, this point 0, n is equal to 1, this pi by 2, n is equal to 2 pi, n is equal to 3 pi by 2. So I'm just writing down all of them in one go. So notice that we have already said there are no asymptotes. There are no asymptotes because whatever questions that we are going to discuss, for them curves are finite. So there are no asymptotes in the polar curve. So before moving on to the drawing the curve, let's plot some values in a table. So I will add a page to plot some values in a table. So, or I will just mention about those asymptotes. No harm in doing that. So no asymptotes as curve is finite. So why this reason is sufficient? Because asymptotes are defined as tangents at infinity. So if there is no tangent at, well, curve does not go to infinity, then what are the tangents? There is no point in discussing such tangents, right? So that's why there is no tangents or there are no asymptotes for this curve. Some tabular values we have already said We have already said we need to discuss the values in the first quadrant only. So I will draw the values of theta and r in first quadrant. So I will plot some regular values along with some unregular values also. So I will start with 0. Uh, I will go for 15 degree, 30 degree, 45 degree, 60 degrees, 75 degree, and finally 90 degree. I'll go for these values. The table for r is equal to a cos 2 theta. So I will open my calci. So a, consider a as it is. So cos of 2 into whatever angle that we want to see. So since we are getting a, notice that we have to multiply by a for this quantity. So we will get a. Now for 15 degree, we have 0.99. So not 1, 15 degree, we have 0.86, 0.86a. For 30 degree, we have 0.5, so 0.5a. For 45 degree, we have 0. For 60 degree, we have minus 0.5a. For 75 degree, we have minus 0.86a. And finally, for 90, we have minus a. So these values are enough because we know our curve is symmetric about both the axes. I'll use these values or this imagination to plot my curve. So again, I'll just move up and I will draw my coordinate axis. So suppose this is my y-axis and the drawing, this is my initial line, that is x-axis. So no need to name them. So first we need to calculate the poles or tangent at my poles. So notice that those were pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So draw these poles. So this is my pole 1. This is my pole 2. So notice that this is theta is equal to pi by 4. Opposite to it, theta is equal to 3 pi by 4. Here it is not 3, it is 5 pi by 4. This is 3 pi by 4. And this is 7 pi by 4. Okay. Now we have maximum radius, that is a. So consider this 4 unit distance or 5 unit distance is our a, or 4. So I will draw a circle with this a radius. So this is my circle of my maximum radius. Now note, mark the points, which were points of maximas. So first point corresponding to 0 and pi, they were a itself. Corresponding to these 2 points, so this one was a maximum point, this one was a maximum point. Later, for points of minima, the value was minus a. So we need to go in the reverse direction. So for theta is equal to pi by 2, notice that this line is theta is equal to pi by 2, right? But since a was taking negative value, we need to plot the point in the reverse direction. Okay. So I will plot that point here. Finally, a point here for theta is equal to pi by 4 because that value is also negative. Now I'll draw the tangents at these points. Notice that tangents were perpendicular to the radial vector. So this is my radial vector and perpendicular to it. So this vector is my tangent vector. This vector is tangent here. This vector is tangent here. And finally, this vector is this vector is tangent at that a comma 0. So I guess I have used all the information. We have used radial tangents. We have used region of existence because we are not going to plot anything beyond this circle. So finally, we'll plot the graph. So we have at angle 0, we have to start here, and while reaching to the 45-degree, we have to reach here with this line being our tangent. And we have to start with this line as the tangent. So we can draw a part like this, draw a part like this. Okay. So notice that after this 45-degree in the table, values are negative. So we are not in the first quadrant itself, but in the opposite direction, that is in the third quadrant. And the value from 45-degree, it starts from 0 and reach till -a. So this part will continue like this and will reach here. So I will use my symmetry or same explanation to draw this part and again this part. Similarly, I'll use the symmetry with my 90-degree axis because that's what we have got from the symmetry. So this point or this part and this part, and I will use my symmetry about my initial line to draw my above part. So this is how a rose curve is drawn. So notice that that's the approximate shape that we have already concluded or we have already guessed. So one more thing, we will just quickly recap or quickly go through all the curves which are polar curves. Some polar curves that we need to remember. Polar curves. So we need to remember those curves like the above that we have discussed and cardioids. Cardioids. So it will have, this will have equations like r is equal to a cos n theta and r is equal to a sine n theta. Here the equations are given by r is equal to a into 1 plus or minus sine theta and r is equal to a times 1 plus or minus cos theta. Okay. So for r is equal to a cos, let's say e1 theta. So some 2n theta we will have, or we'll discuss some particular cases right now. So consider 3 theta odd angle. So for odd angles, we'll have a lip like this, and like this. So we'll have 3 leaves. For n odd, we have n leaves. And if you have r is equal to, let's say, a sine 2 theta, here we have n even, so we have 2n leaves. So this graph will look something like this one. So will look something like this one. Okay. So this is about rose curves. So this is about the rose curves. Now for cardioids, consider the cardioid A into 1 plus cos theta. So notice that it is taking the maximum value at angle 0 and minimum value, that is for cos value, minimum value is -1 at 0 pi. So this part actually moves like this and it is symmetric about or initial angle. So this curve, then r is equal to a into 1 minus cos theta. Here, in this case, minimum value is achieved at 0 and maximum value is achieved at pi. So it will have a shape like this, again symmetric about initial line. So we'll have shape like this one. For other two, r is equal to a 1 plus sine theta. Notice that this curve gives you the maximum value at pi and minimum value at minus pi by 2. Maximum value at pi by 2 and minimum value at minus pi by 2. So this will have this shape, and due to symmetry with the y-axis, this shape can be completed like this. And r is equal to a minus sine theta. Again the same thing, but this time roles will be reversed. Maximum value achieved at minus pi, minimum value achieved at 0. We will have shape like this, and counterpart will be symmetric with the y-axis. So I hope you will remember these shapes. These are really important shapes in Cartesian coordinates. And with this, I will go to the chat section. So if you have any doubt, you can definitely ask. So if you have any doubt, you can ask, or we can end this meeting in 2 minutes. Some are leaving, so that's the message that I'm only getting here. So can we stop here? Can we stop here? So this was the last graph that we have drawn for the Rose curve and Bernoulli, lemniscate of Bernoulli. This was the first graph. Notice that this is the similar graph, or this equation is actually r square is equal to cos, I guess 2 theta. Yeah. So notice that the equation that we are actually drawing is part of our polar curve also. I can give this same equation, same curve in polar coordinates as r square is equal to cos 2 theta. Notice that we have already solved an equation like this one, r square is equal to sine 2 theta in class. So it is quite similar to that one, but we have just converted that into our Cartesian coordinates. So since no one has any doubt, we can leave this meeting here. I'll upload this video and share the link with you by the evening. So thank you. You may leave the meeting. So where is that meeting?